Your model weights may fit on the GPU, while real traffic still crashes it. We'll size the KV cache and calculate how many concurrent requests your VRAM can actually hold. You'll see how to connect the pieces into a workflow that sizes cache memory and returns a safe request limit. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Most teams notice this at the worst possible moment. One inference looks fine. The model loads, latency is healthy. Then traffic grows and the GPU runs out of memory. The weights are only part of the story. Every active request keeps key and value tensors that scale with sequence length and with the number of layers. Good capacity planning turns those hidden allocations into predictable slots. You can either sell or throttle. What we want is simple. Given free VRAM, produce a safe number of in-flight requests that won't OOM, and give knobs to trade latency, answer length, and reliability, so you can pick a max concurrent value that matches your risk tolerance. At a high level, the steps are clear. Measure how many bytes a single token adds to the KV cache across the model. Multiply that per token cost by the tokens in a request to get a request footprint. Factor in dtype choices and allocator rounding to see how many footprints fit into free memory. Wrap the math in a small guardrail that reserves a cushion for other runtime overhead. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we will start by estimating the per token cache cost from a model shape. This snippet turns a model shape into the KV cache memory used by 1,000 active tokens. A single request smoke test can hide this cost because the model weights are already loaded, but every active sequence adds key and value tensors across all layers. The code uses model dtype bytes and headdim to calculate the bytes for both K and V at each token position. The model uses fewer model KV heads than attention heads, which is the grouped query attention case many serving teams see in practice. The visible output shows a per token scaling unit, which becomes the base number for every later capacity decision. Now that we know bytes per token, we need a full request footprint, including prompt and generated tokens. This example sizes one full request instead of one token block. The painful failure mode is that a request reserves cache for the prompt tokens and the generated tokens it keeps attending to during decoding. Prompt tokens and output tokens combine into max tokens. Then the earlier KV bytes per token turns that sequence length into gig. Increasing output tokens raises the upper bound for each active request, which can reduce concurrency even if average prompts are short. Decreasing it can protect capacity, but it may also truncate useful answers. The visible output shows one request's cache footprint, so engineers can stop treating free VRAM as a mystery buffer. Next, we check how dtype choices affect the number of simultaneous requests we can allow. This code compares two cache dtype choices against the same free VRAM budget. The cost and reliability trade-off is direct. A smaller cache dtype can fit more active sequences, while a larger dtype spends more memory per token. Request gib recomputes the request footprint for each byte size in dtypes, and choices ranks the resulting concurrency limits. Safe gib keeps a simple 10% cushion instead of spending every visible gib, which helps avoid brittle plans when kernels, allocators, or monitoring agents need memory too. The visible output shows which cache dtype wins this budget and the resulting hard request count. Real allocators and runtimes often allocate in blocks. Now we include that effect and measure wasted padding. This snippet adds the block rounding effect that shows up in paged KV cache allocators. Real traffic rarely arrives as identical 4096 token sequences. So live tokens uses a small batch with uneven active lengths. Seal rounds each sequence up to block tokens. Then padding PCT measures the memory that is reserved but not holding useful tokens. Larger block tokens can reduce bookkeeping overhead, but it may increase padding for short or uneven requests. Smaller block tokens can reduce waste, though the serving runtime may have its own supported values. The visible output shows both the rounded batch footprint and the padding overhead that capacity plans often miss. Finally, we wrap the math into a guardrail function that outputs a safe concurrency limit for a GPU with known free memory. This example turns the sizing math into a small guardrail a service owner can use before raising traffic. Planned active represents the active in-flight sequences the GPU is expected to carry, not total daily volume or raw QPS. KV limit accepts free gib, max len, cache bytes, and safety, then returns the concurrent request limit after reserving a VRAM cushion. Raising safety spends less of the GPU and lowers the limit, which is usually safer during incidents. Lowering it may admit more requests, but leaves less space for runtime overhead and spikes. The visible output shows whether the plan is safe and how many request slots remain. In a real deployment, you map planned active to the peak number of users decoding at once. You also feed the function the block tokens your runtime actually uses and a batch sample of live token lengths, so padding PCT reflects reality. That single change often explains a surprising portion of missing capacity and leads to smarter auto-scaling. In short, KV cache capacity planning converts per token cache bytes into per request footprints and then into safe concurrent slots. Use it when you serve decoding workloads or when you see OOMs despite loaded model weights. Remember that allocator rounding and dtype choice can change your numbers dramatically. For one concrete next step, log your live request lengths and tune block tokens to minimize padding PCT while keeping the runtime supported block size. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.